Hello, everybody. So today, our guest presenter at the Atomic Scale Design Network series of webinar and lectures is graduate student Rafael Rabida, who is PhD student from the University of Sherbrooke in Quebec, Canada. So his PhD is about the mechanism of organic chemistry, and particularly hypervalent iodine. He's obviously very interested in organic chemistry and computational chemistry, and he's engaged actively in developing software and computational chemistry for education. And that's actually will be the topic of his presentation. And hopefully you like the platform and maybe using it for your own research and education purposes. Hello, Rafael.
Hello, Professor.
Okay, it's all yours now.
Great. I'll share my screen.
Go ahead. Yeah.
All right. You can see all right?
Yeah, I see that. So tell a little bit about the history and current stage of development. It's called CalcUS, right?
Yeah, it's CalcUS. In the origin, it's kind of a collection of all our scripts and ways to be more efficient. And we kind of formalize that into a platform, which we've made open source. So you can view the project on GitHub. We made a publication about it. And you can install it on your workstation or server or whatever and use it for free and modify it. But today I'm going to present in particular the cloud version. So we call it CalcUS Cloud. So the URL is also calcus.cloud. So quite easy to remember. And it's essentially a different, well, it's the same code, but we've adapted it specifically for education. So we focus on the fast calculations using the XTB software here. You can click to see the whole project, but essentially it's semi-empirical tight binding calculations, which are really fast, but give quite interesting results. So in our opinion, it's really ideal for education, where students can run real calculation and get real results that mean something with a fast feedback loop. So
couple of questions along the road. So so how how long this development is continuing? How many people are engaged in development?
Yeah, I've started the project pretty much at the start of the pandemic. So it's been 2 years and something now. And it's, well, for the coding, for the programming, it's all me.
Wow.
Yeah.
Congratulations.
Thank you. Yeah, that was a decent bit of work, but with the pandemic, I had a bit more time and not so many other projects. But yeah, my supervisor, Professor Legault, also helped advise the design and try it out and, figure out the design of the overall platform. But yeah, so it's essentially us two that made all of this. Yeah.
Okay, so one more interruption and I'll let you go and maybe ask a couple of questions along the road. So what level of knowledge, like programming or computational chemistry, for what audience would be the ideally your platform designed for?
Yeah, the platform is really designed for anyone who is interested in quantum chemistry, and specifically for use by professors teaching classes. And we've built it in a way that you don't need to know anything about programming to use it, and you don't need to know much about quantum chemistry. You can learn by doing it. And so, yeah, we basically made sure to make it as easy as possible to start using it and getting results. And with the cloud version, especially because you don't even need to install it. You just need to, well, create an account, but even you can have the free trial, which I'll show in a minute. So it's really, yeah, for beginners and more advanced users if you want to install the full platform.
Obviously, since you're very busy with both programming and your PhD work, you wouldn't be able to kind of like, provide full support like the company does. But for example, if some people are curious and send you the questions, would you be able to provide information how to reach you?
Yeah, sure. If you want to reach me, I think
Oh,
I've
so
added it.
will you do it in the very end? I hope you will provide the slide on this, would you?
A slide on
On your contact information.
oh yeah. Well, here I've added it to the website. You can contact me here contact at the calcus.cloud.
Okay.
Just if you need info or anything, you can also reach us on GitHub on the projects page.
Since I always help people who work with me, so if somebody contact me, I'll give you their information about yourself.
Yeah, sure. Anyone can contact me for if they want to know more about the project or get some calculation time on the platform to try it out a bit more. Happy to just interact with people and have some feedback, really.
So basically, people can do some calculation free of charge on your platform?
Yeah, well, I'll start to show. If you go on the website, so on calcus.cloud, you'll see this page. So here you can see I'm not logged in currently. And you can have a free trial. So here, click try for free now. Will be redirected to a page where here you essentially get 60 CPU seconds of calculation time, which doesn't sound like much, but the calculations really take like a couple seconds. So you can kind of try it out for free. And then if you create a full account, you will get a bit more time. So I'll add the feature to have a bit of computation time every month for free, just to try it out. And yeah, we're working on kind of a bit more advanced plans for using it for whole classes. We're not completely done with that part, but if people are interested, they can contact me. I'll give them some more computational time.
Okay. All right. Well, actually, I'm already kind of get some of information, which is probably in your presentation. You will get it more details. Thank you so much.
All right.
Thank you.
All right. So yeah, so there's a couple terms of conditions. Just it's a free trial. Don't upload any sensitive molecules, etc. And the calculations are kind of considered to be temporary since it's a trial account. Right. So if you click try calculus now, you will be redirected to the launch page here. And then essentially you can already launch calculations. So if we do a very quick benzene calculation, so molecule name, you can specify the solvent. So it's a DCM, dichloromethane. You can see the platform, the text if the name of the solvent isn't recognized. That's kind of a useful feature. Then you can create a project. So my project, and here are the list of calculations. And say I want to optimize to get the structure, and just submit like this. And then it will take a couple seconds to send to the computing instances in the cloud and optimize the structure. So now it's yellow, it's running. And if I refresh, it's already done. So it's really fast calculations, which is, in our opinion, really nice feature for education, for learning how to perform calculations. So here we have the results page. So we have this optimized structure. We can measure lengths. We have here a table. If you have multiple conformers, they will be here together. Here there's just one. We have the energy. And then we have the relative energy for all the conformers, Boltzmann weight. So kind of useful information to have here. And At the bottom, if you perform some other types of calculations, you would have more properties here. I'll showcase this in a bit. So you can already see it's quite easy to launch calculations on the platform. So now I'll log out of this temporary account, and I'll showcase a bit how professors in particular, but also researchers can use the platform. So if you go on register, you have two options. So you have researcher, which is essentially a full account. So this can be a professor or a graduate student or anyone who wants a permanent account. So you need email, password, and prove that you're not a robot. And then you have the students tab. And here you only need two things. So you need a full name just for identification. And you need an access code, which I'll get back to in a minute. But essentially, this is a code which is unique for each class created by the professor. And it allows students to join the class easily without creating a full account, putting their email, confirming, etc. So I'll log in into my own account so I can show you a bit what it looks like on the other side. So this, right. So if I go on my profile here, you'll see there's a couple different things. So there's preferences, which is common for all accounts. But here there's two groups. So there's the research group, which is kind of a more permanent group. So that would be that for a research group. And you have classes, which are kind of temporary and come with a code. So for the research group, you add each person manually. The test class for the class group, you have a code and you can just give it to the students and they can just connect and they will appear here in the list essentially. So here I've created two dummy accounts which are in the group in the class. Then a bit lower, some more information. So the usage of computational time, and here you can redeem codes. So I can create codes and give you the code, and that will give you some more time on the platform. So if we come back to the class here, we see we have two students. So what does that actually do? Well, firstly is that the students will kind of be able to run calculations using the computational time of the professor. So all the calculations they run would be kind of billed in terms of computational resources to the professor. Since obviously they don't have like a subscription or anything, they just put in their name, a code, and they're in, and easily accessible for classes. And the other thing that does is for the professor, you see here we have a tab, test class. So the name would be whatever your class name is. Here we see we have the two STEM students, and we can actually go and see what calculations they have done and what the results are, and kind of debug, help, give feedback, or grade, whatever you want to do. So here we have example molecule, benzene, and you can see I performed on this account also an optimization of benzene. So I can go see the results, see what they obtained, see the log files to give feedback, and same thing here. So yeah, benzene again. So this allows you to kind of, well, for the professor to, get a good feel of the class and how everybody's doing, and helping them without having to kind of physically go next to them and point to things on the screen. So it's a different way of supervising. So now I'll show you a bit more the features about the calculations. So we'll do a quick example of a reaction study. So we'll study the Claisen rearrangement, and we'll showcase the different steps that you can do on the platform. So firstly, I can just draw the molecule. So here would be the substrate. And the reaction will be essentially, will form a carbon-carbon bond here and break the carbon-oxygen bond. And then you can see here the initial structure in 3D. So the drawer created the right structure. We'll give it a name. So, well, it's substrate. It's neutral. Ensemble name, you can add something if you'd like, otherwise it'll be a default name. Let's say we want to study in dichloromethane. I'll create a new project and call it Claisen rearrangement. Right. Here, firstly, let's say we want to optimize the structure. Submit, and then it's going to optimize. Right. So here we have the optimized structure here. Great. So we have the electronic energy. Now, if we want the free energy, we'll just click here on launch calculation on ensemble. So essentially, the ensemble is everything that will be here. And we also can launch on selected structure. Here it's the same thing, but we'll see a bit later the difference. So we want the free energy, so we perform a frequency calculation. We can see the settings were carried over, so we don't need to set them again. That's great. So submit. And there we go. So we see on the page, well, it's the same page. Here it looks exactly the same. Scroll down, we have the free energy. Well, the Boltzmann-Wade free energy. Here we have only one structure, so it's the free energy of that structure. And if we scroll down, we have a new tab here, frequencies. So we have here the IR spectrum based on the frequencies that were calculated. Then we have all the frequency modes. And if you click on one, you get the animation of the frequency modes. And the tab here allows you to change the amplitude of the vibration so you can see it better. So we can see here, this is a CH stretch, etc. And we can analyze these structures. So this is useful, of course, for our transition states. So now let's say we want to find the transition state and the product. So we will do a constrained optimization or a scan and bring these two carbons together to force the reaction. So we launch on this structure. We go constrained optimization between atoms 2 and 3. Scan and from. You can measure here the distance or the angle or also the dihedral angle. So that's useful. And you see when we have a constrained optimization or something that needs the atom indices, they will appear on the structure. So atom 2 and 3, both carbons, from the distance that it is now, 584 angstroms, to something like 1.6 angstroms, let's say. And we can specify in how many steps it will do this transition. So let's say 20 steps. Since these are really fast calculations, 20 steps is not a problem. So we submit. and it's already running. It'll take a couple seconds perhaps. Oh, already done. And then here you'll see in this ensemble we have 20 structures. And here we can see with the relative energy, it starts at 45.7, and it goes up to about 122 here. So we can scroll through the structures and see the reaction. See carbon atoms getting closer. And here is the highest energy structure. And in the next one, the reaction has occurred. So we're past the transition state. So this structure looks pretty close to the transition state. We'll take it and optimize it further. So launch calculation on the selected structure. So actually just this one. And we'll do TS optimization, same parameters. And it will try to find a transition state exactly with the same level of theory. This might take a couple more seconds. And so, of course, it's a couple more seconds, but it's still really fast. So it doesn't really matter in a kind of education context. Still really fast to get results. All right. So let's see if we got the right structure. All right, we can see both bonds are kind of half formed or half broken, if you want to see it that way. So this is great. This looks like the right transition state. To make sure, of course, we'll do a frequency calculation. So here, frequency, submit, and then we get the vibrational modes, and hopefully we have one imaginary frequency corresponding to the reaction. So right. This, we scroll down here, one negative frequency. If we animate it, it looks exactly like the reaction. So this looks like the transition state. So great. Now, one more thing you can do in CalcUS is that you'll see when you do a project, you'll have a bunch of scans, a bunch of failed optimization. You'll have also the things you want to actually analyze. So to really specify what is important, what is final, essentially, we added the flag feature so you can flag things, and then it will show up in like if you want to analyze the results of the whole project, you'll get only the things that are flagged, so you can filter through calculations that way. So we'll go back to the substrate, and we'll also flag the optimized structure. So here, all right, so we have to calculate the barrier, but we'll also calculate the total free energy variation. So we need the product. So we'll go here on the scan, and we'll get the final structure. So this is around the products, almost the product, but we'll fully optimize it to get the ground state product. This. And then we could calculate the whole reaction path. Right, so we'll flag this as well. So, all right, we need a frequency though. And there we go. Now we have the free energy of both the reagent, the transition state, and the product. So we can calculate the barrier and the variation of free energy. So if we want to do that, I'll go back here. So here we have my three projects, have place and rearrangement. So there's a couple of ways you could do this. You could press on this button, which will give you the option to download the files. So here we can see, do I want the just a summary? So the energies essentially and the free energies, or do I want the log files? I can reanalyze. Do I want all ensembles or just the flagged ensembles? So what I define as important, then how much detail I want. So you can download this. It will give you a CSV file, which you can open with Excel or similar software. There's also another way you can do directly in the website. So if you click here to go to spreadsheet, you will have a basic spreadsheet with the values. So this is essentially the CSV file displayed in this spreadsheet online. So if you want to calculate, oh yeah, you can see here we have two default names, so we won't be able to know which one is the reagent. We'll just go back. So we'll click on this one. And we can rename, so this is reagent. And we'll go back to the spreadsheet. All right, so we have reagent here. This is product, and this is the transition state. So if we want to calculate the barrier, we can do equals E16 minus E18. Like this. So, okay, 88.5 kilojoules per mole for the barrier, and the delta G overall, E17 minus E18 minus 46. All right, so it's an exergonic reaction as expected, and we get these values. So this gives you overall the reaction path. So now we'll go a bit into more advanced features you can do. So on this same project, we've drawn a structure, we optimized it and got its free energy. So that gives you a reference. However, we only considered one conformer, which was kind of taken at random. Normally you want to, get a whole sampling of the conformational space. So we'll go back on reagent. You can also click here. And we'll do a conformational search for all the possible conformers. So we'll click here, conformational search. And this will use, again, another software called CREST, developed by the Grimme group, same group that developed the XTB software. So this is also open source software, and it's really useful, to get conformations of molecules. So we decided to integrate it because we use it all the time ourselves. So we'll do a conformational search on this one. And this will take a bit more time because it's a bit more complex process. We'll also, in the meantime, launch a calculation on the product. So yeah, this is the optimized product. And we'll also launch a conformational search. So you're not really limited to one calculation at a time. The computing instances will scale depending on how many people use it, how many calculations are launched. So we can have really calculations in parallel, which is well suited for classes. So that was a bit of the point of using cloud resources. You can just scale and then, not be limited by the machine that runs the software, the server. So, all right. Oh, the first conformational search is done. So, right. So here we can see we have 9 conformers with different free energies, and then we can go see what they look like. And we can see at the end we have 2 for the same energy. Are they the same? Okay, no, they're different. All right. So now we could perform reoptimizations. So by default for conformational search, CalcUS Cloud will use the GFN force field because it's faster, and it allows you to have conformations in maybe like 20 seconds. If you take the default method, it will take a bit more time. So these are not the same level of theory. We need to reoptimize them. And we can all do this in one shot. So launch calculation on ensemble. This will launch the calculation of all 9 structures. So we just go optimize. We could also filter by relative energy lower than X kilojoules per mole, but we'll take all of them. And this will launch 9 calculations. We can do the same on the products. Right, 11, let's just launch on everything. Optimize. Oh, you can see the 9 conformations already done optimizing. And then these 9, which were in the first ensemble, now are were optimized and generate new structures in this ensemble. So we can give it a name. So this is conformers agent, like this. And we can see we have the same numbers, but the relative energies changed, and of course the absolute energies. So we could see a bit what they look like. And we don't have the frequency, so we'll just launch that really quick. Frequencies. And do the same for the products. So this is conformers, product, flag it. Then here we have 2 structures which are mirror images of each other, probably. So let's say I don't want to include this structure number 3. I can just select everything. Oh, these 2 are probably the same thing. These 2 as well. So let's say I just want these selected structure. I can just launch calculation on these structures. So I'll just do frequencies for these and not for the others. Right. So for the frequencies, welcome back. It looks like we busted the default time limit on Zoom, so I'll just wrap up here. So as I was saying, here we have the whole conformers, and for each conformer, we can click and see the individual frequency modes for that conformer. and inspect them, as well as get the weighted free energy here. So go back to the calculations. We see these calculations are done as well. And there we go. So we have the full ensemble of the conformers of both the reagent and the product. So we can have more accurate free energies for both of these species. So we go back to projects and we check the spreadsheet again. Oh, I forgot to run the frequencies of the product. But anyway, we can see this is for all the conformers, and for the reagent we had, it's a bit higher in energy. So we're going to calculate E39 minus E41. So we can see the initial conformer we had is 4.7 kilojoules per mole higher in free energy than the whole ensemble, the most representative ensemble of that species. So that can affect the values you get during studies. So that was essentially what I wanted to showcase. It's a short example of what you could teach using CalcUS Cloud. And we're going to work on building a curriculum. And if you have suggestions, ideas, or you want to participate, that would be awesome. So thank you for watching, and hopefully we'll hear from you soon.